So ideal ideal gas laws. So let's just think about what the word ideal means. So if you're in an ideal situation, maybe you're in the best situation you could be, you say ideally this, right? Uh, what that loosely we can interpret that here as ideally gases are there's a whole lot of variables interacting. So in previous lessons we have discussed the relationship between pressure and temperature, volume and temperature, and pressure and temperature, right? Looking at Boyle's, Charles, Gay-Lussac's law, and we looked at the combined gas law, right? And when we looked at the combined gas law, if you think about the combined gas law, we had PV over T. Okay, yeah, PV over T. And of course you had your initial condition and then your change condition, right? And so you would have this equals the same set of variables the same way, 1 and 2, right? So what we've kept constant throughout everything, even when we talk about combined gas laws, what we've kept constant is the number of particles. So we're assuming that the particles stay the same all the time. But in an ideal situation, those particles aren't going to stay the same, and there's going to be other variables involved. And what we have found is that there is a mathematical equation for the ideal gas law, but what we found is there are sometimes the math does not always give us exactly what we were hoping for, or what we not hoping, but what we're predicting. And so one thing that mathematicians and scientists have been doing for centuries is when you first look at a relationship, you do your best to isolate everything and put it into a testable condition where you've controlled everything that you can think of. You keep everything as constant as possible except for what you're manipulating so that you can observe the response or responses, and then from there we've built mathematical models that represent that. And we've got a pretty good understanding of that. So here's how we can then bring in this constant that we've been looking at with the amount of gas, the number of particles, particularly moles of that. But now we can realize that that can change as well. We could have a varying number of amount of gas. For instance, we could have a situation where pressure it remains constant. We have a way of controlling the temperature. We have a way of controlling a volume container. The volume of the container and things of that nature. But we could change the amount of particles that move in and out of there. So we would essentially be changing the moles of gas, or we expect that the moles of gas changes because of a certain condition. So what we have to do is then take the combined gas law right here, right? And what we want to do is we're going to flesh this out a little bit, right? We're going to flesh this out back into a form like this. So all I did was multiply both sides. I just multiplied it by t, right? So before what we had, so I don't confuse you, let me back up a little bit. So, sorry, let me put that t back. Is we had said that at keeping the moles constant, that this was our relationship for in the combined gas laws, right? And so now let's think about this right here. If I multiply both sides by t now, right, then you should be able to see that we get PV equals our constant that we had, which was the amount of moles, right, times temperature. So now what we're saying is the amount of gas can change. So that means it's no longer K. That means this value here has to change. This value here has to change. And what we do is we use a lowercase n, and n equals moles of gas. So lowercase n or capital N in math tends to represent like the number of something, and depending on which science or math you're you're looking at. It depends on if you use a lowercase n or a capital M. But as a rule of thumb, n refers to the amount of individual particles or the individual things you're looking at. Okay. So now we have PV equals NT. We're almost there. So now we've accounted for the moles of gas. But there's another constant here. And the constant is something that we call R, and that's a capital R. All right? And this R is the ideal gas law constant. And so what we've found is that there is constants in math are like a fudge factor. What they are is we go out so many digits, say 4 or 5 digits after the decimal, and we see consistencies between our relationships, direct or inverse, whatever the case may be. But as you bring more and more variables together, you start getting variations that are hard to account for. And so here's an easy way to put that in perspective. When you've been in math class or your science classes, the more decimal places you go, the more numbers you use after the decimal, the more variations in your value you can get. Now, let's just say you have seven numbers after the decimal. We typically don't work with that many after the decimal, but if you were to use that many every single time, the first 4 or 5 digits, the numbers would be the same. It wouldn't be until you get to the later numbers after the decimal that you start seeing those variations. And we've had problems where that's the case, where we look at the first 3, 4 numbers and they're all the same, whether or not we use, like for instance, 273 or 273.15. So, but when we look at a mathematical model, we're assuming like the best perfect system, but nothing is perfect, which means that there's constant fluctuations in pressure, in volume, and temperature. And materials expand and contract based on those pressures, based on temperature, right? So as a result of that, as you have greater precision of measurement, you go further and further out with more and more significant digits, further and further out with your digits after the decimal. You're going to find more and more variation on those numbers further down in your calculations. And so what we have is a constant that helps account for that, to keep those variations as minimal as possible. And let me show you how we do that. So we just, the way that this equation is basically known is PV equals NRT. This right here is what we call the ideal. This right here is the ideal gas law. PV equals nRT. So pressure times volume equals the moles of gas you have times whatever our constant is times temperature, right? So now let's take this a little bit further. Let's do some learning with this stuff right here. All right. So let's isolate R. Let's just get R by itself. Let's just do that, right? So if we were to get R by itself, all right, let me erase this for you. Let's do a little bit of math. Okay. Let's get R by itself. Just like we have in previous ways, we've isolated our constant by itself to see what the relationship is with those variables. That's what we're doing right here. Let's get R by itself. Let's get this, which we know is to be a constant, by itself. That means we'd have to divide this side by NT. So we'd go away here. So we'd have to divide this side by NT, right? So now what we have is R equals, we have PV over T with the lowercase n. And you should see right here that we're back in the form we had with the combined gas law. Okay? And so now the only thing that we've added in is the amount of moles. How many moles of gas do we actually have? Now that becomes a factor that can change, that can fluctuate. And based on all of these dynamics that are, it means something. So now let's think about this. Sea level, we assume pressure 1 atmosphere. Okay. Let's assume we have 1 mole of gas. Which gas? Any gas. It doesn't matter. Pick a gas. Okay. Now go back on your reference sheet and you'll notice that there's some information here where we highlight. See, there's our combined gas level we've had. I've already given you this equation. I'm just basically fleshing it out and explaining it for you. But 1 mole of gas at standard temperature and pressure, doesn't matter what it is, will take up 22.4 liters of space, right? Standard temperature and pressure being 0 degrees Celsius, right? So we go back here, all right, and so our volume we know has to be, we're going to assume 22.4 liters. And our temperature, standard temperature and pressure is 0 degrees Celsius, but we have to be in Kelvin, so that means we need 273 Kelvin down here on the bottom. Now notice we have atmospheres, liters, moles, Kelvin. Nothing cancels out. Absolutely nothing cancels out. Except for the ones. I mean, the ones do. So essentially what we have, right, is we have 22.4 divided by 273, and you should get right there, right, the 0.08205, right? So you can get, we have 0.082051282. That's what's in the calculator, right? All right, so now let's take a look at this. We've got atmosphere liters on top, and that's how you say that, is atmosphere liters. On the bottom is a 1, and then we have moles Kelvin. No unit has canceled out. Not one unit has canceled out. Okay. So any number by itself is just basically 1, right? And so essentially, you know, we don't need this 1, and we technically don't need that right there. So if you think about it, we've got 0.08205. Wow, that's pretty bad. Let me try that again. Sorry about that. Well, okay. We know that's an 8. I'm going to leave it at that. And then we still have atmosphere liters per mole Kelvin. And this right here, that is R. You will be plugging that value in to this equation up top, PV equals nRT. This is what R equals right here. This is R. So if you go back to the reference sheet that we provided for you, you'll notice that it shows 0.0821. All right, well, so what that means is this 5 has rounded that up right there to be, all right, I know, to be 0.0821. It's assuming that we're going to the greater half, because remember there were some numbers after that 1282, and so it's just by going a little bit higher we're accounting for that little bit more volume that's there. So that's atmosphere liters per mole Kelvin, and so this is the value that we're going to use right here. Now you can use this one right here, but we'll just we can just use that one right there, and you don't have to memorize it because it's literally right there. Now let me draw your attention to something right here. You'll see that this value is here, and then notice moles Kelvin is on the bottom, and so it doesn't matter if you go mole Kelvin, or Kelvin mole. 2 times 4 is the same as 4 times 2. So, x times y is the same as y times x. And so I wrote it this way because if we look at the equation, you've got pressure, volume, and so notice I kept it in the order of pressure, volume, and then down here you have your temperature and preceded by moles. So that's why I kept it mole Kelvin. All right, so I'm just kind of leaving everything in the exact same order that we see in the equation. It's a habit that I'm in, but just know that when you see things online or in textbooks, you're going to see it written kind of in this fashion. It doesn't matter; it's the same thing. But so notice the denominator is the same, but up top, liters is also the same. But notice atmosphere here is millimeters of mercury, right? And so an older standard is literally, if you think about the way a thermometer works, is when temperature changes, you'll get a change in pressure, and that pressure on a thermometer, that is scaled out, and the scale is scaled out like literally measuring how many millimeters of mercury does that thermometer increase or decrease. So that's where that comes from, right? And then right here, kPa, that's kilopascals. So the easiest way to explain this is the distance between you and someone else might be 6 feet. Okay. Well, if you were to measure that in inches, well, if there's 12 inches per 1 foot, that's 72 inches, right? And so 72 inches, 6 feet are both the exact same value. They're the same distance, but the numbers are different because we're using a different unit. So that's really all that has happened here. So 62.4 liters millimeter mercury per Kelvin mole is the exact same as this. So this is one form of the R value. This is another form. This is another form. Which one do you use? Well, the only difference is the pressure. So if pressure is given in atmospheres, you're obviously using this one. If pressure is given in kilopascals, you're obviously using this one. If pressure is given in millimeters of mercury, you're using this one. That's the only difference, okay? That is it. But you'll still get the exact same answers. You'll get the answers you're supposed to, but those answers will be adjusted to account for your pressure unit, okay? And so you just have to get used to interpreting that. There's some lab equipment that we will use where we're going to measure. We'll measure what's going on within the system, and the equipment that we'll use, the pressure measures it in the kilopascals, and so we would then, in that situation, have to use 8.314 in all of our calculations, not the 0.0821. Okay, that's all that means. All right, so there you go. That's kind of the basics of that. Let's just wrap this one up, and then I'll do another video where we kind of do some calculations with it. But you can see that this is a fairly easy equation. I mean, you almost don't need help doing this. I mean, PV equals nRT. I mean, it is such a direct relationship. You've got this equals that. It's basic plug and chug. The only thing that might be a little confusing to you is how to do some calculations where you have R. But if you do what your Algebra 1 teachers have taught you, and you rearrange your equation to solve for the missing variable, and then you plug everything in, and you multiply and divide, add and subtract the way that you're supposed to, well, in this case, you're just multiplying and dividing, then units will cancel out properly. If they don't cancel out properly, then that's how you know that you're mathematically doing something wrong. And so you would backtrack and ask yourself, wait a minute, so I'm trying to multiply here, but my units aren't canceling out. Wait a minute, what did I do wrong? And you're probably going to find that you should have moved the variable in a different way, and you should be dividing, or vice versa. Okay, that's really about it. All right, let's go ahead and end this video, and then we'll go from there. Bye. Have a good one.